Well, I think we're just about there. Welcome back, everyone. Before we get started today, any questions that folks would like to begin with? Okay, well, just as a reminder, one thing you want to check out on the Moodle website is right under the top under grades, we had an additional extra credit opportunity for the showing up on Halloween pretty much. Usually Halloween is really low attendance, so that was a great day. Just about everyone showed up. But if you check here, take a look at the column that says Halloween extra credit. A 1 means you were present on that day. And if you see it's incorrect, just let me know and I'll be sure to correct the record right away. So what I was saying is it's going to drop the lowest quiz at the end of the semester. The syllabus already says we're dropping 3 lowest, so that's bumped up to 4. And there was a question asked earlier by Michael that what if we have a perfect 10 on all of our quizzes? Some people are in that situation. Extra credit feels kind of meaningless, but I made a note of that and I'll see if I can come up with some other opportunity along those lines for people who wouldn't be benefiting at all if I drop a quiz on their grade. But that's my announcement so far with where we're at. We're in section, oh, where are we? This thing gets really long towards the end of the semester. We're in section 6.1. We're doing the second half here. And I got a little bit nervous that we might finish way early today. I felt like these problems will take a little bit longer. So just in case 6.2 is here, I wasn't trying to get very far on these, but just in case we have a ton of time on the table, it's available now. Also, quiz number 11 is posted. And quiz number 11 is a little bit strange once you take a look at it. Let's take a look at it right now. That's probably a good way to start off class. It says, well, first there's a simple interest formula that came out of nowhere. We're going to be working on formulas like these. The notes is focusing primarily on the compound interest formula when we have n compoundings per year, say 12 if it's monthly, and then the exponential equation. But this is also using the simple interest formula, and we have 3 different columns here. Let me see if I can zoom in where that looks a little bit better, more readable. On column 1, we're trying to find the money after 30 days if it was simple interest. This one is asking for the amount of money we'd get after 30 days if it's compounded, let's see here. Annually, we could do on this one, and monthly on this one. So 3 different computations, and it's really going to be 2 formulas. The first column, we'll just use simple interest as a formula. And their other remaining columns, we'll use the compound interest formula here. So I was thinking to start off today, how about we just do the simple interest as an additional problem between examples 4 and 5, and then we'll take a look at the bigger formula. Does that sound all right to folks? Okay, so let's take a look. I'll just steal the formula right off the quiz. It's not plagiarizing if you're plagiarizing yourself, right? That's probably an English teacher question. They're probably going to say yes to that question. So let's put that over here. Let's just invent a really simple scenario that's going to use this formula right here. Again, this is pulled right directly off your quiz. So you don't necessarily have to write it down right away if you don't want to. But for our scenario, let's suppose let's take $2,000 is loaned at, let's say, 2.5% simple interest for 5 years. So imagine maybe someone like a grandparent is giving you a loan for $2,000, maybe fix up the car or something like that. And getting a loan from a family, it's a pretty common thing that if they're going to charge you interest, and some family members would, it might be simple interest. They're taking a little easy on you if they did do that. And let's make the question then be, how much is owed after 5 years? And this is going to be a really common assumption, since we're not looking at the more fancier amortization formulas where you're making payments regularly throughout the loan. We're just wondering, if we made no payments whatsoever, how much are we on the hook for after 5 years has gone by for the original 2,000? So how much is owed after 5 years? Let's put here, assuming no payments have been made. This sounds like a pretty bad thing to do. I mean, if you borrow $2,000, we should probably be paying it off as we go, but let's assume we never pay a cent of that money back. It sounds like an awful person already. This is how much we'll have to owe in the simple interest situation. First, let's break down what this formula is saying. The A of t is going to be the account's value after time t. So for us, it's going to be the amount owed from the original amount of 2,000. P is going to be the initial value. And that initial value right here is going to start looking a lot like this initial value, familiar in the notes. So think of that as the initial value, and you're not too far off the right track. In fact, our functions are going to start looking like this when we're thinking about interest. So back down to here, or, geez, I lost my place. There we go. P is the initial value, and that's what this 2,000 would be in this really fast problem we're writing down. 2,000 is the initial amount that was borrowed. R is going to be the interest rate. And so our value for R is not really the 2.5%. If we use that as a number, our values are going to be way, way off. We have to use R equals 0.025. All I did is take a decimal place right here, shifted left 2 places, and we're changing the unit from a percentage just to a decimal number back over here. So that's the interest rate we have. I'll still highlight this because that's where we got that information from when they said at 2.5% simple interest. Then this t variable right here, that's just going to be the value after t years. It's the input to the a function, a for the amount at time t, and it will go right there, multiplying the interest rate. So that's a breakdown of the entire function. And to get through this problem, I'd probably just really do 2 steps on it. Step 1, write down the function that we're about to use. It's amount at time t equals a principal 1 plus r times t. Then step 2, we'll fill in the information for this function. Amount at time t is now equal to, take the $2,000 principal. It's going to be multiplied by, let me move this pane over here out of the way. 1 plus now the interest rate. So let's put in the 0.025. And we've almost got it. Just throw in the variable t. And that's the setup of the function. We want to know how much is owed after 5 years. So that's going to be our time variable that we're going to plug here and here on our very next step. I said 2 steps, but I guess you could think of that as 3 steps really. Here's the 3rd step, depending on how you number them. So the amount owed, that's A of something, we'll put in 5 years, is going to be $2,000 to start, but now it's multiplied by 1 plus 0.025, multiplying 5 for 5 years. So that's what happened to our time variable. And now at this stage, it's just a matter of throw it all into the calculator, see what we get out of this thing. Any questions at all first, folks, with putting that formula down to this here? Okay, so that's simple interest, and now for fast calculator, let's use this thing. Pretty much you can type this in verbatim. It can go 2,000 multiplying 1 plus 0.025 times 5. And so the value came out at $2,250. That doesn't sound too bad. The interest rate was low on this thing, but if interest was compounding, we would be on the hook for even more money. That figure would be higher. Let's put down our answer, 2,250. And that's essentially how the first part of the quiz is going to go. We'll use that same formula up here. We'll have 10,000 as the principal amount that's being invested. And we'll use simple interest at 3% for our first computation. We need to find out the amount right here after 30 years. So you'd be plugging in the information, put 30 right here, and crank our way through it. So that finishes off the first column. But now we have to do it again with interest compounded monthly and interest compounded annually. So same kind of things going here and here. Well, we'll have to look at the compound interest formula to get through that kind of thing, but any questions at all, folks, with the first example? Okay, so fortunately, this kind of situation only owing $2,250, at best, that's probably something you might get from a relative who's being kind. If it was Wells Fargo, they are absolutely going to compound that interest, and every other bank, even a Westmark bank, your friendly local credit union, is going to be a lot rougher on this. They're going to use this formula right here for the amount owed. So let's make that our next problem. I mean, it's next in line, so we ought to. It looks similar to our old formula. Let's bring that down just to compare temporarily. Our old formula went this way for simple interest. We have an amount at time t equals a principal amount. So far, that's matching up. Principal would go right here. We have an interest rate. Our interest rate is in the same location, but now our time variable goes out here in the exponent position. It becomes an exponential function all of a sudden if you're compounding interest. So now it's really appropriate for this section for sure. And I'm going to take, well, let's keep that yellow highlighting. I'll leave that there. Next thing is new is N. N is going to be the amount of times you've compounded in 1 year. So for an example, if we said compounded quarterly, this would mean N equals 4 quarters out of the year. If it says maybe something like semi-annually, compounded. I don't know why, but that one always kind of mixes me up. Anyone know how many times you'd be compounding if it says semi-annually? Exactly, that would be 2 times. And if it says monthly, that would be 12. If it said daily, 365. It could also be compounded on the minute if a bank just really wanted to do that. It's a fast computation. It could be compounded on the second as many times as you want. If we let that variable n get larger and larger, the formula will change on us. So we'll have a next formula that we're going to take a look at. But as far as the quiz goes, it's this formula here for simple interest and this one right here for compound interest. That takes care of the entirety of the quiz. So the information here is still the same as before. A of t is the amount at time t. T is going to be assumed to be a time variable in years. P is the initial value, sometimes called the principal amount. But I'll usually say initial value, since that's going to match up with the directions our formulas are about to go. R is the percentage rate that we've highlighted, or APR if they ever say those words. But don't forget, it has to be a decimal. Might as well highlight there just to emphasize. And N is the number of times you'd be compounding. So let's practice this right away. It says here on example 5 for a scenario, Keith deposited $4,000 into an account with 2.4% interest. Already they're giving us most of the information right there. That's the principal amount or the initial amount. Here's the interest rate. Just don't forget it must be in decimal form. And they told us it's going to be compounded 4 times a year or quarterly. So N equals 4 there. I put this here in the parentheses, not just because it was also in ALEKS, but if I brought this question on exam 3, I would be specific what I mean by semi-annually or quarterly and so on. So that's not necessarily portion of the problem that you should lose points on. So part A says, just write a function that expresses the amount in Keith's account after t years. All we do is go to the amount at time t, fill in the information. So here's how it reads. I'll go left to right on the formula and write amount at time t equals. Next stop is the principal amount, which was $4,000. Then 1 plus interest rate R right here. We look that up. It's at 2.4. So take the decimal, scoot it 2 places left to write it in as 0.024. Next, we divide by the number of compoundings. That's going to be 4, going right here where the n variable was. Now we can close the parenthesis. Right up in the exponent position, appears here once again. So here's n, and it's multiplied by time t. So that's our entirety of part A. We just write it in like that. And these are typically not simplified. And honestly, it's a good idea not to, because if you leave it in this format, it's clear that we invested 4,000 initially. It's even more clear what the interest rate is. It's right there as a decimal. And down below, it tells us how many times it was compounded. If we were to simplify everything inside, we would have hidden all that information. It would not be clear how many times it's been compounded necessarily, unless you looked over here and is there, but it would also be hiding the interest rate. So this format is pretty decent to just stop right here. Yes, go ahead.
Would the end also be 4?
Oh, yes, absolutely. Thanks for mentioning that. I should have put both of 4 here and here. I must have just been copying the formula a little too strictly. So 4 should go right in that spot. Thanks for catching it. Other questions so far? Okay, then the follow-up question, these are actually pretty fast problems. It's more just being familiar with the formula that gets us through them. Follow-up question says in part B, assuming no withdrawals are made, let me fix that thing there. How much will he have in the account after 6 years? So we can write out amount at time 6 coming from the 6 years equals, we could probably just drop color coding at this point since we have the function in the right format. 4,000 goes here, 1 plus 0.024 divide by 4. Then up in the exponent position, it's 4 times 6. Or if you put it in a 24, that'd be just fine as well. So this is the exact amount of money that Keith has. It's the right answer. And I would give essentially all of the credit if this is on your paper. I would only take off a half a point if we got the wrong answer in the calculator. So think of this as essentially the whole partial credit for the entire problem, writing down what's about to go into your calculator. Next, well, we really have to put it in the calculator, so let's do that on our next step. If you're getting an amount different than I am, let me know and I'll be very happy to help out. We'll work through it together and make sure we all get the same value here. So I'll use Desmos calculator just because it's fast and available. And in Desmos, I would type this in as if I really was using a TI-30 X2S. I'd put in 4,000 in that calculator, 1 plus, then 0.024, divide by 4, close the parenthesis, and for the power, this has to be written as a 4 times 6. Desmos is weird. If I go 4 times 6, it puts the 6 in the wrong spot. So if you really want to get it in there, you need 4 times 6 with parentheses, and same with your TI-30 X2S calculator. Make sure you have parentheses there, or if you just put 24, that's a little bit more safety, I'd say. So let's take a look. After 6 years, Keith has $4,617.55. We're assuming he never made a withdrawal, so that's that statement right down there. And so that's how much is sitting in the account. Go Keith, I want to be his friend, but let's put down 4617.55. And if it's dealing with money, we can always safely assume we're rounding to the nearest cent. So nearest hundredth and whatever you see in your calculator. Well, any questions, folks, on getting that number? Anyone getting something different, or should we spend a little more time on this one? Okay, I've been mentioning if you do this in the TI-30 X2S, you can type it in as one line. But if anyone's here today and you're using a more complicated calculator like this one, I really hate this calculator. It's a little bit trickier, but if you're used to this, let me know. I'd be happy to show how it ought to go in this calculator. Anyone here today use a big fan of the TI-30 XA? Me neither. Okay, let me know though if you'd like to see it done. I'd be very happy to help out. So we're getting that amount there. And then that's pretty much the whole question. Part C is just asking a related question. How about after 60 years? The interest rate is, again, pretty low on this, so we didn't get anything amazing after 6 years. This is actually losing value due to the interest rate being higher than the amount of interest he's earning. But if Keith forgot about this account, maybe developed dementia or something like that, after 60 years, we'll be able to find out how much money's left there. In the calculator, this is really fast, but on paper, I would want to write down this whole thing all over again. I'm only changing what's highlighted in yellow. So in this parenthesis, it's still 1 plus 0.024. Divide by 4. Now 4 times 60, or 240 would go there. Then it's pretty much already in your calculator. Go to your last operation and insert a 0 right there. Done. So it's kind of nice to have a calculator for this. Now it's up to $16,810.30. Got a different number. Let me put this down and see if we can agree on the same number. 16,810.30. Oh, that's an interesting sign. Yeah. So we're getting something really, really big. And just a question for you. What kind of calculator are you using? Awesome. That's one of the, I don't even have that nice of a calculator available for us, but this one would be similar. Let's use the good old TI-84. This one's not allowed on exams, so that's the only reason I don't use it a whole lot, since it's better to use a calculator you expect that you would use on an exam. But the way I type this in, it'll look similar to what actually goes into the TI-30X2S. I mean, it's still Texas Instruments. First thing I'd put in is 4,000. And this should look very similar in your calculator as well. A 1 plus, and I just learned this trick. Alpha y equals inserts fraction if you hit enter there. It's not required, but it makes it look a little bit nicer. Let me get that in a little bit bigger. 0.24, then a 4 here. Then I have to go up arrow. Go, you found it? Gotcha. A 1, say like right here. Gotcha. So 4 times 60. And you wouldn't think that caused such a big problem, but if this becomes a 1, then it's unbalanced with the 4 here. That's why it got so large. So enter on this. We're getting the 16,810.30 cents after rounding. Does that look right to folks so far? Okay. So either way we do it, we should be getting about that dollar amount. And what's kind of interesting, once we get into chapter 6, all of a sudden the calculator becomes the thing we're practicing a lot. That won't be all of chapter 6, but here and there, it's going to be computationally intensive through the calculator. So definitely practice those in class. And when you're doing the analytics, try to imagine like you're doing it on a real exam. Use the calculator you would bring to an exam. And that would be really great extra practice if you're worried about getting these into a calculator. And also, I'll remind folks about this. I say it a lot. If this is on your paper, I'm really happy with that. If this was a 5-point problem and I messed up this, maybe I got something wrong, you're pretty much going to see that. I'm only going to take off a 0.5 point on a real exam and a real quiz if it's correct right here. That's really because if you're in an exam setting and you're just a little bit nervous, it's so easy to miskey something, even if you know exactly how the problem should go. So that's why I created partial credit that way. So after, oh, I should fix that. After 60 years, there's 16,000. After just 6 years, there was 4,617 in the account. Well, any questions at all, folks, on getting through this one? Okay, so that's this function here. When you go to do it on the quiz, let me see if I still have it pulled up. This column will be compounded annually. So that's where you'll have a 1 right here and a 1 right there, just 1 compound per year. The next one is asking compounding monthly in this column. You would just put a 12 here, a 12 there, and then you'll be in great shape. And what you'll notice is the amount here will go up if you compound, what was it, annually. But if you go and compound it monthly, the value goes up again over here. And it starts to ask us a natural question. Is there a limit to that? We could check it out on Desmos even. On Desmos, we increase the number of compoundings, let's say to 12. Now that's annual, and now it's $16,858. Let's take a look. Hey, that's about, well, I mean, it's not amazing, but we've got like $48 extra by increasing the amount of compoundings. we decide to compound, let's say, every day of the year, 360, 365, 365, then we're up to 16,881. That's like 70 extra dollars. I mean, that's not amazing, right? Over the course of 60 years, you got 70 extra dollars for compounding every day, as opposed to, what was this, quarterly. But what's kind of amazing is this can keep on going. You could say, let's compound 10 to the power of 50 times per year. That's just an obscenely large number. That's more than compounding per second. And something broke on this. I think the number's too big. It got a little offended. Let's maybe drop that down to 10 power 10. That's a little bit more what I was expecting. So 10 to the power of 10 is a very, very large number. We're over 1 billion times compounded. 16,883. It's going up, but there's diminishing returns to that, right? It's not very impressive after a minute, but it's interesting to know you can compound every instant of time if you wanted to. If you keep on compounding, something happens to the 1 plus r over n, which is kind of strange. Oh, I'm skipping a little bit too far ahead. We obtain the number e when that happens. So if the compounding keeps increasing, this whole thing turns into about 2.718282. Really kind of strange. And that means the whole function here changes into an ordinary exponential function, like the one on the very, very top of the notes. Its base is going to be that number e. But sorry, I kind of skipped a little bit ahead of that. We should definitely do example 6 before we take a look at those new formulas. Any questions so far, folks, on getting through this one? Okay, let's try out the next one down below. This one's kind of a silly situation, but this is a very shockingly real-world situation that's happened to me. It's happening to me right now. It says, suppose that a $12.50 cup of coffee is purchased on a credit card with a 26% annual percentage rate, so 26% APR. That's about right for the economy we're in right now. Assuming no payments are made towards that $12.50 purchase, how much is owed after 5 years? So imagine you have a pretty high balance on one of your cards. You bought a coffee at $12.50, but you kept that high balance for around 5 years until it was paid off. We could say on the last payment over 5 years, that's the final payment that includes the last $12.50 for that coffee purchase. So how much did we actually pay in interest for just the $12.50 is what this question is asking. We can calculate this and write out the amount at time t is going to be a principal amount, 1 plus an interest rate r divided by n, the number of compoundings, raised to the power of n times t. So this is pretty much the strategy. Write down the formula and try to fill in this information, the initial amount or principal value. You also need the interest rate. We're going to have to find out the value of n as well as we go. So let's take a look. Anyone spotted what the initial principal should be? It'd be the $12.50, absolutely. So P equals $12.50. The initial charge on the coffee, it looks like it was an expensive one, probably extra buzz shots or whatever they call them. Here it said 26% annual percentage rate. So that's definitely the interest rate R. Let's write it in as R equals 0.26. That's a huge interest rate, but it's typical for a credit card these days. And it says next, well, just annual percentage rate, assuming no payments are made. There's no information here saying it's compounded anything differently than annually. So we can assume on this one, n equals 1. That's probably not realistic for a credit card company. Credit card company's probably going to compound monthly. But it was never indicated in this problem. It just said annual percentage rate. So I think that's a safe assumption on this problem. So our function becomes amount at time t equals the $12.50 that was charged. We're not going to make any payments toward it for 5 years, but we also need to put in 1 plus 0.26 The n is a 1, so we can drop the value down there. And up here, it's n times t, but that's just going to be t altogether. So that's how it comes together. The question says, how much is owed after 5 years? That's going to go in for the time variable and those locations. Does that look right to folks so far to that step? Okay, let's plug in the information and then this problem is done. Okay, that's why I got a little bit nervous on these notes. It looked like there's a lot of problems, but when I actually went to practice them, they're pretty fast. There's not a lot to do on these. So amount after 5 years is A at 5. It's going to be equal to the 12.50 that we put in, 1 plus 0.26, and then 5 would go right exactly here. So now we're back to a calculator. That's all we have to compute right here. So let's grab this fast calculator once again. 1250, then parenthesis, 1.26 if you like, is a little bit faster to type in. Raised to power 5. That doesn't look quite right. Raised to power 5. Oh, sorry, I didn't see the decimal right there. I thought that's way too much money. It's 39.70. So after 5 years, that coffee really costed $39.70. I mean, that's not terrible, right? But that was just one charge over the course of 5 years not getting paid off. That accumulates. That starts to really feel like you're bleeding cash every month, paying these heavy bills. But it gets even more interesting because this is an exponential equation, right? This grows exponentially. What if it was not 5 years, but let's say 15 years? Any guesses how much this is going to jump if we increase this by 3 times as long? Would you say it's in the hundreds or the thousands or worse? It's really hard to say, right? It is an exponential function, so eventually its graph goes like this. It just shoots up. So let's put it in 15 years, excuse me. We now owe $400 on the 1250 purchase. We increase that another, let's double it. Let's say 30 years. Maybe we held that credit card for a really, really long time, but we always kept a balance. There was always more than 1250 on the card. Then after 30 years, you owe $12,824 for that 1250 coffee. That's really very shocking, but so is the time frame, right? 30 years is a long time to hold the balance on a card. It gets ridiculous if you say, like, what about 60 years? That's now, oh geez, $13 million, $156,571.19 for your 1250 coffee. So it's truly exponential growth, but the time frame is also huge. We have to admit that as well. So that's that equation again. Any questions so far, folks, on getting to that answer, the 3970? Yeah.
For the first formula where you plug in everything, you just included t, like the exponent.
Right up here, yeah.
Just t because n equals 1, so it's just going to be automatically 5.
Exactly. It was really like 1 times t, so just simplify to that. Same with the denominator right here. It's really 0.26 divided by 1, but then it just simplifies to that as well. And then I simplified again when I threw in the calculator. I left it in that format, but then I just added the 1 and the 0.26. Other questions so far? Okay, well, that's the shocking way exponential growth happens for a $12.50 cup of coffee, or you can imagine how bad that would be if you put down a down payment on a car loan for a few $1,000s. That's probably even a worse decision, but that's how life goes sometimes. Sometimes we just have to get by. Next thing we're going to take a look at, again, is that number E once again. E is kind of mysterious here. It emerges in strange locations. It's approximately 2.718282, and it's irrational. This decimal expansion never will repeat, and it'll never terminate. And it comes from here. This is exactly the things we're looking at when we're calculating the compound interest formula. This thing, as n increases without bound, turns into E itself. Well, let's show that. On Desmos, it's a pretty fast experiment. We can put in first the number E. Let's take a look at what its value is going to be. That's 3. Let me try again. So there's y equals E. It's 2.7182 and some change. Here on the graph, it's a constant function right at that height, and it becomes a horizontal asymptote for us. Next thing we'll put in is that equation. So it is y equals 1 plus 1 over n to the power of n. Looks pretty bad over here, but remember, n is supposed to be a positive number, greater than or equal to 1. So let's give it the right domain so it doesn't look so crazy. So that's our function. And the function 1 plus 1 over n to the power of n has a horizontal asymptote. As you move this red dot further and further to the right, the height is getting closer and closer to 2.7182. You can make it as close as you want by simply going further and further to the right. Eventually the black line, which is the number e at a horizontal line, and this thing, they're just going to overlap. They'll never touch exactly, but again, you can make that as close as that you like by making n larger and larger. That's what they're saying here, as n increases without bound, this in the limit becomes that number e. And that means this whole portion right here, the whole thing, excluding the variable t, that one is spared, turns into this. A equals P-E-R-T. Well, all the thing that happened is the thing in the middle we just replaced with E, and that's our formula for compound interest if you are compounding continuously. What this means now is n was going off to infinity. The number of compoundings, kind of hard to actually even express, but we can say the principal or the amount is compounded at every instant of time is the interpretation for this thing. And that's kind of a weird thought, right? It's not saying it's compounding every second. It's compounding every millisecond or every half a millisecond. You have to keep on refining every single interest of time. In every single time instant, a compounding happens. We could say it's compounding infinitely many times, essentially, yes. So really weird function, but this equation right here, whether we express it in that format if we're thinking money, or in this format if we're just thinking of exponential growth and decay, this thing here is the same as the original function we were looking at the very, very top of the notes. We're back to this. Only thing that's changed is the base b is now the number e, Euler's number. So here's our new situation. Whether we're using P for principal or A for the initial amount, we're talking about the same exact function. So A is the initial amount or the initial value of some quantity. R is going to be, we said interest rate before, but we were just thinking about money, and now R could be anything. We're going to call it the continuous growth rate per unit time. If R is bigger than 0, then we really mean growth. There'll be a continuous growth function. And R could be negative. When it's negative, we think of it as continuous decay as a function. So if we plot those, just to get a quick feel for what those formulas are saying, here's what it would look like. I'm just going to put in a generic equation. Y equals, let's make A be a 3, e to the power of, let's make it first be 0.5 times t. All right, let's reset that graph as well. This is what our graph would look like with the value 0.5 is bigger than 0 for our growth rate. It blows up like this, kind of like the $12.50 coffee becoming millions of dollars after 60 years. But if it takes a negative value, throw a negative here, this is what the exponential decay would look like. Yeah. Yes, that function never changed upon differentiation. It's a very, very weird one. There's no other function like it. And so in certain senses, we think of E as the most special base for any exponential function. It's sometimes called the natural base. And when we talk about logarithms, we'll call it a natural logarithm. It's because of those reasons you're mentioning. Once you start looking at average rates of changes and start talking about derivatives, that is a really weird function. Doesn't seem so much so far, but the more you look at it, the weirder and weirder it's going to get. Any other questions so far, folks, about this model down here? Okay, so far what we've done is we've taken this equation that we asked what happens if the number of compoundings n increases. If that happens, all of this turns into e. But then we're taking this whole equation, p times e to the power of rt, and we're going to let it work for anything. A of t is going to be the amount of money. If we're talking about money, or it'll be the amount of a population, if we're talking about population size, or it could be an amount of mass, if we're talking about a mass of some kind of radioactive isotope, something along those lines. So these equations now work for everything that could be modeled as continuous growth or continuous decay. Now let's try it out right away. Example 7, again, even though the equations look strange, these are very, very fast problems. They're kind of fun in a way. It says, we're back to money, $27,000 is borrowed for 7 years. That would be the initial value. At an interest rate of 5.5% per year, that's going to be the growth rate, because now we're thinking positive. We should highlight 7 years. We're going to have to throw that into the function. I would say the most important word is really right here. Compounded continuously. When you see that word, whether you're in ALEKS or doing a quiz or doing an exam problem, this is what we're thinking about. Continuous growth or continuous decay. That means we're using this function. So just those words, compounded continuously, is indicating this is the right function to use now. So we'll write down the amount at time t is going to be a e to the power of rt. We need to fill in the value of a, the value of r, but we have those values. They're staring at us on the paper. It now becomes amount at time t equals $2,700 e to the power of, let's take a look. It's not 5.5. Don't forget to always convert your percentages into decimals, or else your values are going to be really, really wild. So 0.055, then multiplied by the variable t. So that's our new function. And the good news about this is, honestly, it's just faster to put into your calculator anyways. So if you see something that's compounded continuously or growing or decaying continuously, this is easier than the compound interest formulas we were using earlier. We want to know, well, it said find the amount owed, assuming no payments are made until the end, and it's been borrowed for 7 years. So now we're getting to the answer. The amount in 7 years, that 7 is going to be plugged into the same 2 locations inside the function and then in the output of that function. So it's now 2,700 e to the power of 0.055 times 7. So that's what it looks like just before going into the calculator. Any questions at the moment, folks, with the expression down here? Okay, well, let's calculate it and see what we get out. All you need to put in is just the right-hand side. So it's 2,700. And in your calculators, let's find out where that actually lives. We need E itself. I think we have a screenshot somewhere. Let me take a look here. Oh, there it is. So here's our screenshot. Let's just cite it once more. So back in the calculator, to get your base E, hit your second key, the natural logarithm key, and it pulls up that e to the x that we're expecting. So in Desmos, it's still going to look about like this. You could just literally type in an e, and you've got the right value. Go up to the exponent position, and I'll use parentheses to make sure when I go and put times 7, it stays in the exponent. So 0.055 times 7, and the initial value of $2,700 after 7 years becomes just about $4,000 altogether. 39, 67, 96. How's that look to folks? Anyone getting slightly different answers? Awesome, glad to hear that. So if you're getting these same values right here, you're going to be in great shape for the ALEKS problems and quizzes and exams. Yeah, go ahead.
Sorry, my brain is just blank.
No worries.
So I think I'm only asking this because I know this on the calculator.
Mhm.
Whenever we use E in general, can you only have E if there's an exponent on it?
Oh, that's a good question. It turns out you don't have to. In your calculator, yeah, when you press this key, it comes in as E. I think it'll go like that, right? Something along those lines. But you should be able to just delete all that, put an E, and you'll get the number. Or if you wanted to, you can go E power 1, and that's a default way to get just E itself as well. Other questions so far? Okay. So we've got the value, and again, really fast question. It feels like we should be doing more with it. We are used to like 20-minute problems, it feels like. But that one is now completely over. Let's see what else we have here. One more example. And this is pretty much the end of the notes. So let's see what this is saying here. A biologist has a 114-gram sample of a radioactive substance. They never told us what it was. That's no fun, but we'll have some interesting isotopes when we get into exponential decay later on. They ask us to find the mass of the sample after 6 hours if it decreases according to a continuous exponential decay model at a relative rate of 14% per hour. So the questions, they just sound really awful when you read them. Well, let me show you how I would think about this and what I would do if I saw it as a problem, say on a quiz or an exam or anything like that. Here's where I would look first. Let me read through it again. Find the mass of the sample after 6 hours if it decreases according to a continuous exponential decay model. Let's also highlight decreases right there. That's enough information for us to say we're using this. An amount, this time it's going to be an amount of mass of, the mass was 114 grams initially. So the amount of mass at time t is going to be A for initial mass. It says continuous exponential decay model, so we'll have E to the power of R times T. But when it says decreases, this also says R is negative. So let's take a look if we can find those values. First thing we're going to need is the value A right here. Has anyone spotted what A should be in this problem? Good call. That's the initial mass right here, 114 grams. Next thing we definitely need is the value of R. It is right here at 14% per hour, but it has a directionality this time. If they say something is decaying and they also say decreases, the value for R is really this, negative 0.14. We still have to decimal shift to make it a decimal from the percentage, but now we're also forcing it to be negative altogether. And the notes, this is also where you could be looking. If it ever says continuous decay, it's telling you immediately your R value must be negative when you go to put it inside the function. So back to our function here we're building. We can now fill in the values that we have and say the amount of mass at time t is going to be first the 114 grams. I'll drop units until we give the end answers on this one. Then it's going to be the base E exponential. R here, we're going to put in as a negative 0.14. And then multiply by t for time. So that's our entire function. It says next, well, what was the question? Find the mass of the sample after 6 hours. So they gave us a time information. And that's what's going to be plugging in here and here. We'll just plug in the value of 6. Then the whole question's over right at that stage. So let's write out amount at mass at time 6 hours is now 114 e to the power of negative 0.14 times 6. It's back to the calculator, but this is a pretty fast one as well. Let's wipe that out and put in just that right-hand side. 114 e to a power negative 0.14. Oh, and I messed up. Again, watch out for this mistake. This is a really easy one, especially in Desmos. If I hit times 6 right here, that's not right. That 6 is in line with 114. That means it's no longer an exponent. So we have to backtrack off that answer. And the one fix in this calculator, at least, is put parentheses in. Good call in your calculator as well for the exponent. Times 6, once I finally hit it, right here gives us, well, we start at 114 grams. It decays at 14% per hour. So after 6 hours, we have just less than half of that. That does feel plausible in this situation. So it's 49.21 grams. We made a pretty big deal out of the negative sign in this problem. It came from the directionality of saying decreases, decay model. But honestly, it's really easy to spot if we made a mistake. So if I forgot the negative sign, this is the answer I would have got. 114 grams would decay to more than double its initial mass. We would know already that that's not right. The mass is not increasing all of a sudden. Radioactive things disintegrate suddenly. That would tell us, oh, there just needs to be a negative, and that's what fixes it, making the answer look actually plausible. Well, we did it, folks. That's the end of all of these notes. Any questions or comments at all? Okay, well, let's save these off. And with what we're doing next is, we're just going to focus on a little bit more about exponential functions, paying major attention just to their graphs this time, their domains and ranges, because now we're ready to transition over to the inverse to that function right there. We're going to call it a logarithm, and we'll have a natural logarithm. We'll also, if the function is, say, like this one, this is a base 2 exponential, we'll have a logarithm base 2, so we can invert those as well. So we're trying to invert every single exponential function that we see, and that should be plausible, because if we look at the graph, those are one-to-one functions. They pass the horizontal line test. Every function we're about to plot is going to have that property. But let's take a look at them and see how it goes in full. So here's our section 6.2. It starts off just repeating information we have already been discussing. Here's our core definition for what we mean by exponential function, this thing right here. Like before, there's really special values to definitely pay attention to. A being the initial value is something that just comes up repeatedly. Knowing how it comes up is sometimes all you need to do to answer a question and save a whole problem. Don't like the way I highlighted that. Let me just go like this. The base B has to be any positive number that's not equal to 1. And I don't think that's necessarily highlight worthy here. And so our goal now is, let me fix that. We just want to plot these functions. I forgot to space this out apparently, so let me put some extra space here. I think the version that's actually on Moodle does have the space put in if you print out that version. So these instructions are very similar to what we're actually doing in the ALEKS system. It says graph the function. We were going for at least 5 points. We'll go for exactly 5 points on ours. Draw the asymptote using a dashed line, and then we'll state the domains and ranges. So this is really just a tour of exponent laws in a certain sense, like we mentioned before when we plotted our first one. And here's how we can get through it. Let's start with a XY table of points that goes like this. So y equals f of x, but let's just pen in exactly 5x is the function. And really good values to pick should be values that are not too far away from 0. 0 being the initial value is something you can definitely put on your page. But if one of your values is like 5 or 6, that's probably not good because a 5 or 6 suddenly becomes a very, very large number in this context. So I probably would always start at around -2. Then start increasing until we have 5 values. I'll always want to do the initial value 0. This one's really just a freebie. It's 5. So you get 1 point automatically for free on this problem. Then go over to +1, +2, And that's pretty much how I'm going to do every single one of these tables. Again, it's kind of like doing a parabola. The very first point you want to put in is the x coordinate of the vertex, because you never want to move too far away from the vertex of a parabola, or your y coordinate gets too large positive or too large negative, and we can't even plot it. So that's why we're always sticking really close to around 0 for these sketches. Then over here, the plot could look about like this. And one thing you're allowed to do if you're doing this by hand is you don't have to have the same scale horizontally as you do vertically. So what I'm going to do is I'm going to stretch out the horizontal scale and go -1, -2 this way, +1, +2 this way. But in the vertical direction, let's compress it down. That's pretty much how you would plot it anyway. You would change the scale going this way and going vertically just so you can see the whole graph or the interesting parts of it. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, really wanted a 15 on there. But you're also going to find sometimes, even when you do this by hand, you'll have all the coordinates, but not all of them are even going to fit on the graph. That's okay if that ever happens to you. Just put on your graph the coordinates you can fit on there and draw the line through those, and that's going to be just fine. Well, let's start this off. I put down a 5 here because that's what it should be, but let's put in the explanation as well. The x value you're putting in right here where x is, so it becomes 5 to the power of 0. But that's an exponent law. 5 to the power of 0 is automatically 1. Anything to power 0 is 1, except for this thing. 0 power 0 is undefined for really bizarre reasons. We can't actually calculate that one. But here we have a value. Now we just have to do the remainder ones. Let's start with a -2. This will turn into a 5 to the power of -2. And we have to correct that exponent to get a value out. Negative exponent takes your base 5, puts it into a denominator. So now it's 1/5 squared, and then it becomes a 25th. So at -2, we're trying to plot a 25th. That's really, really hard. I'd probably just put a dot that's essentially right above the x-axis. Try not to put it on the x-axis, because one important fact about exponential functions is that 5 to the x, or any base, is going to be greater than 0 for all x. So it never even hits the x-axis on this thing. Now, next value we'll put in is a -1. That one is tough to plot as well, but here's how it goes. It's 5 to the power -1. We correct the exponent by putting 5 in the denominator. And so we get 1/5. 1/5, I can do a more honest point, but still it's pretty much right there on the x-axis for that next one. Our next value is at 0, 1, or hang on. Yes, 0, 1 right here. I said it was 5, but I think I made a mistake. I was thinking of the value right in front when I highlighted that, thinking of 5. Let me take that off there. Oh, geez, not too much off. Let me actually highlight this in blue. That was the base I should have been thinking of. And the initial value is really just a 1 that's right in front. So that's what we're actually plotting right here when we put in the 1. Sorry for that mistake in that location. It's good to put in this value here just to be specific sometimes. Does that make sense on the problem that was over here? Okay, so next, put in a 1. It's just 5 to the power of 1, but let me fix that there. That's an exponent. That just gives us a 5. So right up at 1, we have a point here at height 5. Put in a 2, we have 5 squared, so we're at 25. That means at 2, we're like somewhere up here. I can't even plot that point. Wouldn't even fit on the document. But that's okay. We'll just draw this the best we can. The whole curve would look about like this. Right around here is the turning point where it just takes off. Kind of like how the $12.50 coffee suddenly became millions of dollars after compounding. For this function, it's blowing up really massively the moment we cross the initial value is when it makes a big turn. So that's finally y equals 5 to the power of x. And we have to do a couple more things. We want an asymptote, and we'll do a dashed line with that. One thing that's interesting about an exponential function is they all have a horizontal asymptote, guaranteed. There'll never be a vertical asymptote, but there's this one for sure. This is at height y equals 0. That's why this is so hard to plot out here. It's getting very, very close to the horizontal axis rapidly, much more rapid than the other functions we've been dealing with. But out here, it's just blowing up. I want to put an arrow here over here just to say it is going to the left forever, and it's going to the right forever. So we can also say that the domain, it's just going to be all real numbers on this thing. We can say negative infinity to infinity. That's what Alex expects. Or you can use a fancy shorthand if you're doing this on paper. That version of R is saying all real numbers as well. The trickier one is range on these things. It's kind of interesting. Every exponential function has that as a domain. So that's like a freebie. It's like a polynomial. The domain is all real numbers. But range is a little bit tougher on this thing. We have to be careful. Anyone see what the range should be? Exactly. I like the way you said 0 not included. That means it has to come in exactly like that. And good call. It never actually hits y equals 0. And so that's why we have to put a parenthesis. There's no actual value of 0 in the range whatsoever. But because 0 is not in the range, it also means this. 5x equals 0 has no solution. So some exponential equations are unsolvable immediately. And that's because the 0 that's right here, that came from the horizontal asymptote, which our curve never touches. It's missing in the range. You can't even solve that equation. That's kind of bizarre. We did it, folks. That's our second sketch of an exponential function by hand and further analysis for domain and range. Let's add a couple notes here. All exponential functions have this domain. So that's great. That means the domain is a freebie kind of question, including in Alex quizzes and exams. Range, we'll have to be careful. But let's also mention right here, we found a horizontal asymptote. That's also something that happens for every single exponential function. So we'll say all exponential functions have horizontal asymptotes and no vertical asymptote. So the situation we see here on this graph, that's pretty much every situation. The only way we can make the graph look a little bit different is if we start messing around with it. If we say add +3 to the function, the whole graph goes up by 3, including the horizontal asymptote. If we put, say, 1/5 of x, like that, well, the whole curve is going to flip around the y-axis. It turns into a reflection out of nowhere. And so although this is the basic shape that we're expecting, we're going to also be looking at a few transformations of this shape as well when we go through the notes. Well, any questions at all, folks, on this one here? Okay, this is pretty much how they look like in Alex as well. They're pretty fast to get through, but this is the careful step right here, just working through the exponents. How about one more for the road? Does that sound right to folks? Okay, let's give one more a try. Here's the weird one out of nowhere, part B. And we can say part G when we come back, say, on Tuesday of next week. Don't want to do all the fun problems. But with the same instructions, let's try out this one next. Let me copy these down just for reference. So when you look at this function, it's very similar to the one we were just dealing with, where it was 5 to the power of x. But let's blow this just based off this information right here. This is a reflection across the something axis. It's been a while since we talked about transformations, but they're definitely coming back, and it's a good idea to talk about them since we'll need to review some information as we get closer to the final exam. But anyone recall what this one does? Is this about the y-axis or does it go about the x-axis? Kind of easy to forget with these kinds of things, but there's a trick to this. If the negative appears around x, my gut instinct is, sounds like an x-axis reflection, but these are tricky problems. It's actually not true. It's the opposite of what we expect. This one's a y-axis reflection. So this should reflect across the y-axis. But we should see that when we go to run through the problem. So let's give this a try and see if that's what really happens. Let me just put an arrow here instead. So we need a fast table with 5 values. Like before, we could start with x at -2, -1, 0, 1, and 2. And extra lines there just to make sure we can work out the value. The y-coordinate is h of x, and we can pen in 4 power -x like that. And there's a lot of things you could do with that exponent, but I think for this problem, it's just easy enough to put in the values up in here and see what happens. So first put in -2. We'll have 4 to the power of -2. Already that's pretty tricky, right? We have double negation. This is turning into 4 squared, giving us a value of 16 in. Next, throw in -1. It's 4 to the power of -1, which means that's 4 power 1. And exponents mean repeated multiplications, but that analogy will break down. 4 power 1 is just 4. Next, we're putting in 0. So it becomes 4 to the power of -0. But the opposite of 0 is still 0. That's even a weird thing to write down, although it is a correct statement to make. Still, it's 4 power 0, and that's just a 1 then. Next value we put in is a 1, and now it gets a little bit different. We put a 1 right here. It's now 4 power -1. We need to put that down in the denominator. It's 1 over 4 to the power +1, or just a 4th. Do it again at value 2. It becomes 4 to the power -2. This transforms into 1 over 4 squared when we fix the exponent. And so now it's 1/16 altogether. So that's our table of values. Yeah, go ahead.
Being the last one we did on this one,
Yeah,
is it consistent that, because the fractions and the whole numbers are just opposite from one another? Like the 1/5 is opposite to 5.
exactly. Yeah, it's the reciprocal in this sense.
that's
Yeah. And so, yeah, that's something you will see as a pattern in these kinds of problems for sure. Yeah, here we had at 1, we get a 4th. On this one, we had to get to -1 to get a 5th. Only reason that happened that way is the exponent was positive on this one, but negative on this one. So we're seeing the 1/4 on a different side of the table this time. But yeah, that is a pattern we would see on all of these.
So if you were to get like 24, positive 24 is 1, could you assume that you'll have a 1 over 24?
Yes, absolutely. Yeah. Other questions about that so far? Okay, well, let's put this down on the graph and see if we get the real reflection that we're expecting. Oh, let me try again. There we go. I'm going to make the graph kind of look like this, a little bit different, because we're noticing all of our values are positive. We might just focus on quadrants 1 and 2. Then I'll do the same trick as before. This will be -1, -2. So I'm expanding my horizontal scale. +1, +2 here. And the highest value we obtained is 16. So I'm going to compress the vertical scale to try to get to at least 15 tick marks on this. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So now we've got the scale. All we're doing next is just plotting in these values. This time at -2, we are at a higher height. It takes on value 16. Oh, I didn't quite go up to 16. So we would be up here for our initial point. At -1, it drops all the way down to 4. So it's dropping rapidly and massively. At 0, we get exactly 1. So it's crossing right through here. Now, these are the hard ones to plot. We have a fourth. A fourth would be about like that. And I'm not sure I can really plot a 16th on this reliably. I mean, even if I zoomed in, I really can't plot it well. So I'll just make it look like it's just about touching the x-axis, about what this one's doing. So now our curve would look about like this. It comes through in a smooth, continuous way, and I'm trying to draw it so it actually looks like a horizontal asymptote down there. That's kind of hard to do. Let me try one more time. This will be my last do-over. That'll work. Again, they don't have to be perfect. Just try your best on these. If it looks like it seems a little bit funky there, I understand. These are hard to plot, especially when the numbers get so close to 0. So here's y equals 4 to the power of negative x. And yeah, that is a reflection. If that power was positive, it would have looked like this instead. But throw in a negative x, and this is what you get, a reflection across the y-axis of that other curve. It still has a horizontal asymptote, which we need to plot. It's through here. Y equals 0 is our horizontal asymptote. Add domain and range, really just a formality at this point, right? We can say domain is all real numbers. I'll just use interval notation on this thing. And the range is going to be the extent of all the y coordinates are every positive y coordinate. We just cannot take on 0. Well, 0 is neither positive nor negative, so all the positive coordinates or values would look like that. 0 to positive infinity is the range on this one. The next graph that we're going to take a look at when we come back on Tuesday is a much more wild. It has a negative here. That's a reflection about the y-axis. This 1/3 doesn't look like it, but it's a reflection across, or let me start over. That negative there, I think I said backwards, is a reflection across the x-axis. Sorry for that confusion there. This 1/3 turns out to be a reflection across y-axis, because you can write 1/3 as 3 power negative 1 to get 3 to the power of negative x. It really has a reflection. It's just hidden on this thing. It's kind of bizarre. And then the -2 is going to drag the whole graph down by 2 units, taking the horizontal asymptote and messing with the range. So that'll be the one we look at when we come back. So any questions at all, folks, on these 2 quick graphs that we produced? Okay, definitely a good stopping point for us then. These are pretty longer questions. And when we come back, we'll be getting through section 6.2. We'll also be probably starting section 6.3 on Tuesday as well. That's going to be a longer section. We're kind of past the introductory ones where the problems were a little bit shorter. But have a great weekend, folks. If you have any questions, I'll be in the tutoring room as usual. Otherwise, I'll see you all on Tuesday. There you go.